Hello everyone. So today we will start isomerism. First we will see the definition of isomerism. What is isomerism? Isomerism is compounds having same molecular formula but different in physical and chemical properties. Physical and chemical properties are known as isomers. And this phenomena of compound existing in different molecular showing different physical and chemical properties are known as isomerism, and this phenomena is known as isomerism. Now there are many types of isomerism, so we'll see what are the types of isomerism. First, isomerism is divided into two parts: a structural isomerism and configurational isomerism. Okay. Now, in a structural isomerism, isomerism have same molecular formula, so it will have same molecular formula, but different structural formula. A structural isomerism will have same molecular formula, but different structural formula. What about configurational isomerism? Configurational isomerism will have same molecular formula and same structural formula also. If a structural formula will be different, then it will come into a structural isomerism. Understand? So it will have same molecular formula as well as same structural formula. Then what will be different? It will have different configuration. Same molecular formula as well as same structural formula. Now configurational isomerism also divided into two parts. One is stereoisomerism and another is conformational isomerism. Next, a stereoisomerism is also divided into two parts. One is geometrical isomerism and another is optical isomerism. But in today's class, we will study a structural isomerism, and the structural isomerism is also divided into 6 parts. So first we will study chain isomerism. Then we will see ring chain isomerism. Next, we are going to study positional isomerism. After this, we will study functional isomerism. After this, we will study metamerism. and in last we will study tautomerism. Write this all in your copy. In today's class, first we will see a structural isomerism. So first write the definition of a structural isomerism. First we draw this, then we have to write the definition of a structural isomerism. Now what is a structural isomerism? Same molecular formula, compounds having same molecular formula, compounds having same molecular formula but different a structural formula. Or you can say how structural formula are different. Different connectivity of different atoms. So you can say different connectivity of atoms. Are known as a structural isomers. Are known as a structural isomers. And this phenomena is known as a structural isomerism. And this phenomena is known as a structural isomerism. Okay. In this case, we note down. You can make a note. One point, very important point, that in a structural isomerism, if 2 or 3 compounds are showing a structural isomerism, they will have different IUPAC name. Why they will have different IUPAC name? Because of different connectivity of atoms. If connectivity of atoms is different, their name will also change. No? So a structural isomerism will have different IUPAC name. All a structural isomerism will have different IUPAC name. Note down this. In a structural isomerism, first we are going to study chain isomerism. You can pause the video and note down all this. First we are going to see chain isomerism. Again, isomerism it is, so molecular formula is same molecular formula. Same molecular formula. What else is same? Same functional group. Same functional group. Then what will be different? Then only something will be different. Then only it will show chain isomerism. So, what different number of carbon atom, different number of carbon atom present in parent chain. Then it will be called chain isomerism. First example we will take example number 1, C4H10. C4H10, we can draw C4H10 like this also. This is C4H10, and we can draw C4H10 like this also. Same molecular formula, no function group is present. Now we do the numbering 1, 2, 3, 4. 1, 2, 3, 4. So in this case, number of carbon atom in parent chain is 4. In this case, number of carbon atom in parent chain is 2. So these two are chain isomers of each other. These two are chain isomers of each other. Next example we will take C4H10O. So we can add alcohol here. Now, in this case, we know we will start from the main functional group. Main functional group is alcohol. 1, 2, 3, 4. Here, we will start from here. 1, 2, 3, 4. Same molecular formula C4H10O. Same functional group alcohol, but different number of carbon atoms. In this case, number of carbon atom is 4. In this case, number of carbon atom in parent chain is 3. So these two are chain isomerism of each other. Third example we will see C4H. You see, in this case, we will start from the 1, 2, 3, 4. 1, 2, 3, 4. Same functional group. Alkene is present. Same number of carbon atom. In this case, number of carbon atom in parent chain 4. In this case, number of carbon atom in parent chain 3. So they are chain isomers of each other. Fourth example we will see. See, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same functional group present. Same molecular formula. But if we select parent chain in this case, parent chain will be this 1, 2, 3. 3 carbon is present. In this case, in parent chain, 1, 2, 3. 4 carbon is present in the parent chain. So these two are chain isomers of each other. Similarly, fifth. In this case, parent chain is this 1, 2, 3, 4, 5. In this case, parent chain is this 1, 2, 3, 4. Same molecular formula, same functional group, but different number of parent chain present, different number of carbon atom present in parent chain. So they will be chain isomers of each other. I hope everyone understand what is chain isomerism. Same molecular formula, same functional group, but different number of carbon atom will be present in carbon parent chain. Then they will be chain isomers of each other. Next we are going to see ring chain isomers. Next is ring chain isomer. Ring chain isomerism. What is ring chain isomerism? Again, same molecular formula. Molecular formula will be same in all the cases. Same molecular formula. Same functional group. same functional group. Then what will be different in the case of ring chain isomerism? But different cyclic and acyclic segment will be present. But different cyclic and acyclic segment will be present. So in this case, if you see, so in note you can write, if cyclic segment is present, if cyclic segment has to be present in the ring chain isomerism, so at least the compound which will show ring chain isomerism will have at least 1 degree of unsaturation. The compound which will show ring chain isomerism will have at least 1 degree of unsaturation. Compound which will show ring chain isomerism will have at least 1 degree of unsaturation. 1 DOE. Example we will see. First example, C4H8. You know, in C4H8 it is alkene, butene, degree of concentration is 1. First we will take C3H6. C3H6 propene, degree of concentration 1. So it will have 1 pi bond or it can have 1 ring. So these two are ring chain isomerism. In this case, acyclic segment is present. In this case, cyclic segment is present. So these two are ring chain isomerism of each other. Second example we will see C4H8. Again, degree of constitution in this case is 2. So now in this case, this we can take 1 ring. In this case, we will take 1 3-membered ring and 1 methyl group will attach. We can take 1 4-membered ring. So these 3 are ring chain isomerism of each other. A, B, C. A and B ring chain isomerism. B and C ring chain isomerism. A and C are also ring chain isomerism of each other. B and C how ring chain isomerism? In this case 3-membered ring. In this case 4-membered ring. 1 methyl group is present. So different cyclic and acyclic segment is present. So B and C will be also ring chain isomerism of each other. I hope you understand this. Third example. This you can also draw like this. We can also draw like this. In this case, 1 pi bond is present. Hence, degree of unsaturation 1. 1 ring is present. Degree of unsaturation 1. 1 ring is present. Degree of unsaturation is 1. So this A, B, and C, and function group is same. Alcohol, alcohol, alcohol. So these are also ring chain isomerism of each other. See, they all have same molecular formula, but different cyclic and acyclic segment. So these A, B, and C are ring chain isomerism of each other. I hope everyone understands what is ring chain isomerism. Next, we will move to positional isomerism. positional isomerism. What is positional isomerism? In the case of positional isomerism, same molecular formula will be there, same functional group will be there, same parent chain will be also there, same number of carbon atom will be present in parent chain. Then what will be different in positional isomerism? In positional isomerism, same molecular formula, same functional group, same number of carbon atom in parent chain, same number of carbon atom present in parent chain, present in parent chain. Then what is different? Position of but different position of functional group, multiple bonds, that is double bond, triple bond, and substituent in the compound. Then they will be solved positional isomers. Then they will be called positional isomers. See, very important, how it is different from chain isomerism. Same molecular formula, same functional group, but also same number of carbon atom present in parent chain. Why is different? But different position of functional group, double bond, multiple bond, that is double bond, triple bond, and substituent. We'll see example. First example we take. I have attached alcohol on this carbon. In this case, I have attached alcohol here. Now, molecular formula is same. You know this C4H10O. 1, 2, 3, 4. 1, 2, 3, 4. Same number of carbon atom present in parent chain. But if you see, position of alcohol in this compound is at first position. In this case, position of alcohol is at second position. So these are positional isomers of each other. Second example we will see. In this case, if you see, again we will start numbering from here. 1, 2, 3, 4. 1, 2, 3, 4. So if you see, in this case, positional isomerism starting from carbon 1, like if it, number of carbon, molecular formula is same, number of carbon in parent chain is same, functional group, that is alkene. In this case, alkene is present at first position. Here, alkene is present at second position. So these two are positional isomers of each other. Third, if you see, start numbering from here. 1, 2, 3, 4. 1, 2, 3, 4. Again, same number of carbon chain, same molecular formula, same number of carbon atom present in parent chain, but position of alkyne is different. So these two are positional isomers of each other. Fourth we will see. Now in this case, if you see, now we will start from here. 1, 2, 3, 4, 5. In this case, you can start the numbering from any side. 1, 2, 3, 4, 5. So you notice, in this case, this substituent is present at second position. In this case, this substituent is present at third position. So these two are positional isomers of each other. Fifth and last example. case it will be 1, 2, 3, 4. So again, same molecular formula, same functional group, ketone, ketone, but number of carbon atom in parent chain is different. So they are not position isomerism. Then what are they? They are chain isomers. These are chain isomers, not positional isomerism. Next we will start functional isomerism. Fourth is functional isomerism. Now what is functional isomerism? Again, molecular formula is same, but different functional group is present in the compound. But different functional group, functional group will be present. Same molecular formula, but different functional group. By example, we will see. First example. See, molecular formula is same for this compound. C4H10O. Here alcohol is present. Here ether is present. So they will be the functional isomers of each other. Second. Again, if you see molecular formula for these two compounds will be same. It will be C4H6. But in this case, alkene is present, and in this case, alkyne is present. So they are functional isomers of each other. Third. See, molecular formula for all these three compounds A, B and C are same. But in this case, ketone is present, in this case, aldehyde is present, and in this case, alcohol is present. So they are functional isomers of each other. Again, molecular formula for these two are same only. Why is this? They are ester and this is carbonic acid. So they are functional isomers of each other. Different functional group is present. In this compound, ester is present, and in this compound, carbonic acid is present. So they are different functional isomers of each other. In this case, just you have to only check if they have same molecular formula and different functional group. So they will be functional isomers of each other. Next. See, same molecular formula. This is 2 degree amine and this is 1 degree amine. And we know this, we have studied in nomenclature that 2 degree amine and 1 degree, 3 degree amine, 2 degree amine and 1 degree amine are different functional group. So these two are also functional isomers of each other because they are different functional groups. all have same molecular formula. A, B, and C all have same molecular formula, but they have different functional groups. This is 1 degree amide, this is 3 degree amide, and that is 2 degree amide. 1 degree amide, 3 degree amide, and 2 degree amide. 1 degree amide, 2 degree amide, and 3 degree amides are different functional groups. We have studied this in nomenclature. We can note 2 or 3 important points. I am telling. First, you can note this, that alcohol, phenol, and ether are functional isomers of each other. Make a note and write first point, that alcohol, phenol, and ether are functional isomers of each other. Second point, you write that ketone and aldehyde. Ketone and aldehyde are also functional isomers of each other. Third, you can write ester and carboxylic acid. Ester and carboxylic acid are also functional isomers of each other. Next, you can also write nitro and nitrite. Nitro and nitrite are also functional isomers of each other. So first point, alcohol, phenol, ether are functional isomers of each other. Second, aldehyde and ketone are also functional isomers of each other. Third, carboxylic acid and ester are also functional isomers of each other. Fourth, you can write nitrite and nitro are also functional isomers of each other. Next, we will see metamerism. That is fifth. Metamerism. Again, molecular formula will be same. In this case, we will see metamerism will have same molecular formula, same polyvalent functional group. What is polyvalent functional group? Same polyvalent functional group. But what is different? Same molecular formula, same polyvalent functional group. What is different? But different alkyl group attached with polyvalent functional group. Different alkyl group attached with polyvalent functional group. First, we are going to see what is polyvalent functional group. So first, we will see monovalent functional group. Monovalent functional group. So in the case of monovalent functional group, what are the monovalent functional group? Only one alkyl group will attach. OH, monovalent functional group, alcohol. Thiol, monovalent functional group. Amine, NH2, 1 degree amine, monovalent functional group. Aldehyde is also a monovalent functional group. Carboxylic acid, monovalent functional group. Amide, CONH2 is also a monovalent functional group. Divalent functional group. Divalent functional group, which can attach with two alkyl groups. So you know ether. Ether is divalent functional group. Thioether is also divalent functional group. 1 degree amine, 2 degree amine. 2 degree amine can attach with two different alkyl groups. There is also a divalent functional group. Aldehyde, ketone. Ketone is also divalent functional group. This is carboxylic acid and ester. Ester is also divalent functional group. Amide, this is 1 degree amide. but 2-degree amide is a trivalent functional group. Now what is trivalent functional group? It can attach with 3 alkyl group. Trivalent functional group. So 3-degree amide and 3-degree amide are the trivalent functional group. Next we will see the examples. First example we will see of ether. See, this side of ether, this is propyl and this is methyl. This side ethyl and ethyl. See, in both the compound, different alkyl group present on both sides of divalent functional groups. Na? So this is called, these two are called metamer of each other. Second, again same molecular formula but different alkyl will be present. So these two will be also metamer. If I draw one more in are this A, B and C, between A, B and C, A and B are metamer of each other. Same functional group present, same covalent functional group. Molecular formula of A, B and C are same. A and B same functional group present, different alkyl group is present. But are A and C are functional group? Are A and C are metamer of each other? No, they have same molecular formula. But here it is 3-degree amine, and this is 2-degree amine. This is also 2-degree amine. So you know 2-degree amine and 3-degree amines are different functional group. So these two are functional isomers of each other. A and C and B and C are functional isomers of each other. In this, A and B are metamer, but A and C are functional isomers, and B and C are also functional isomers because 2-degree amine and 3-degree amines are different. Same molecular formula, different functional group will be called functional isomers. Next example we will see third. These two are same molecular formula. This is also 2-degree amide. This is also 2-degree amide, but different alkyl group present. So these two are metamer of each other. Fourth, this is important. Now tell me, are these two metamer of each other or not? These two are not metamers. Why? See, because this cyclohexyl group is connected with oxygen. Here also cyclohexyl group is connected with oxygen. Phenyl group is connected with carbon. Phenyl group is connected with carbon. They are same compound. No? If you rotate this whole compound, they will overlap with each other. So these two are same compounds only. So they are identical. They are not metamer. They are identical. Now tell me about this one. Now these two compounds are metamer of each other because here carbon is connected with phenyl group, here carbon is connected with cyclohexyl group. So in this case alkyl group is changing, different alkyl groups are present in both the position, different alkyl group is connected, attached with polyvalent functional group. So these two are metamer of each other. Now tell me, is this two are metamer of each other? We can argue that these two are, this side propyl group is present, this side methyl is present, this side ethyl, this side ethyl. So different alkyl group attached in both the compound. So these are metamer of each other. These are metamer of each other. But you can also argue, okay sir, position, like same molecular formula, same number of carbon atom present in parent chain, same functional group, and but position of functional group is changing. So these are also positional isomers. Na? So in those cases we have to see priority order. Priority order, through that priority order we will decide which isomerism is this. So what is the priority order to check isomerism? Right, in the note write priority order to check isomerism. So first we will check if ring chain isomerism is present or not. If ring chain isomerism is present, then that will be ring chain isomerism. Second, we will check tautomerism. If tautomerism is present, then that compound will show in tautomers. Third, we will check functional isomers. Functional isomerism. Fourth, we will check metamer. If they are metamer of each other, then you have to write metamer. Then we will check chain. Then we will check positional. You know, in priority order, positional is coming in the last. So if it is single correct question, we have to give that they are metamer of each other. If it is multi correct question and both options are given, metamer and positional, then we can take both metamer and positional isomerism. Understand? In single correct, we have to give it is a metamer isomerism. It is showing metamer. In multi correct, positional and metamer both can be correct. Next, we will study tautomerism. See, here we are not going to study tautomerism in that detail. We will study tautomerism in more detail after completing GOC. Here I am just giving you definition. What is tautomerism? The last one, 6. Tautomerism. What is tautomerism? See, such isomerism, such kind of isomerism is arise due to oscillation of monovalent atom and a structure obtained when a solution of monovalent atom takes place, a structure obtained in this case are called tautomers. A structure obtained are called tautomers, and the phenomena is known as tautomerism. And the phenomena is known as tautomerism. Okay, so we'll see. Like after we will study GOC, and then only you can understand tautomerism better. That's why we'll teach. That's why I will teach tautomerism after completing GOC. Just I am giving definition. So such kind of isomerism arises due to oscillation of monovalent atom, and after oscillation of that monovalent atom, a structure obtained are known as tautomers, and the phenomena is known as tautomerism. We will see an example. So this hydrogen, this monovalent atom, this hydrogen will oscillate on this oxygen, and this double bond will come here. So structure obtained will be this: CH3, COH, double bond, and CH2. Now these two are tautomers of each other. You can say, sir, these two are functional isomers of each other also, because in this case it is ketone and in this case it is alcohol. But according to priority order, first you have to check if they are tautomers or not. If they are tautomers, it means they are not functional isomers. So these two are functional isomers of each other. And this hydrogen will oscillate from here to here continuously. So they are in dynamic equilibrium. They will be in dynamic equilibrium with each other. Now this is ketone, this is called keto, and this is alkene plus alcohol, so it is called enol. This is called keto-enol tautomerism. Keto-enol tautomerism. There are many other tautomerism also, which we will study in more detail after completing GOC. I hope you understand what is tautomerism. At this definition, that such kind of isomerism arises due to oscillation of monovalent atom. In this case, monovalent atom is hydrogen, and the structure obtained are called tautomers, and the phenomena is known as tautomerism. Now we will do some question on structural isomerism. First question: calculate number of carbon atoms. Number of carbon atoms. Calculate minimum number of carbon atoms. Calculate minimum number of carbon atoms required to show chain and positional isomerism. Chain and position isomerism in first you have to show me in alkane, second alkene, second alkene, and third alkyne. Pause the video and do this question. Calculate minimum number of carbon atoms required to show chain and position isomerism in alkane, alkene, and third alkyne. Okay, I am doing this now. I hope you have done after pausing this video. So alkane. In alkane only single bond is present. So we will see how many carbon atoms, minimum number of carbon atoms required to show chain or position isomerism. So if you take two carbons, this will not show any type of position any type of chain or position isomerism. If you take three carbon, again it can't show any chain isomerism. If you take four carbon, now if you take four carbon, you can draw also like this. Now parent chain 1, 2, 3, 4. Parent chain 1, 2, 3. So parent chain is different. Same molecular formula, same functional group, and parent chain is different. This is showing chain isomerism. So minimum 4 carbon atom required for chain isomerism. Second, position. How many minimum carbon atom required to show positional isomerism in the case of alkane? So if you take 3 carbon atom, it will not show any positional isomerism. 4 carbon atom, see, you have taken 4 carbon atom and it is showing chain isomerism. So if we take 5 carbon atom, can it will show positional isomerism? You try to do this. Now again it is becoming chain isomerism only. If you take 6 carbon you place here and 1 carbon you added here. Now in this case 1, 2, 3. Okay. Now we will start from this side. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same molecular formula. Number of carbon atom in parent chain is same, but position of substituent is different. So these two are positional isomers of each other. So minimum number of carbon atom needed will be 6. Next, in the case of alkene, how many carbon will needed for chain and position isomerism? See, for chain isomerism, again, till 3 carbon, it will not show chain isomerism. If you place this double bond here and here, it will be same only. So we will add 1 more carbon. Now in this case, what we can do? We can add this carbon here. Now, in this case, in this compound is containing 4 carbon atom in parent chain. In this compound is containing 3 carbon atom in parent chain. So these two are chain isomerism of each other. So minimum number of carbon needed will be 4 only. 4 carbon. Next, position isomerism. We have to see how many minimum number of carbon needed for position isomerism. So if we take 4 carbon and we can change the position. This one is easy. 1, 2, 3, 4. 1, 2, 3, 4. Same molecular formula, same number of carbon atom in parent chain, but position of alkene is different. So 4 carbon will needed. Now in the case of alkyne, minimum number of carbon needed for chain isomerism and for positional isomerism. Alkyne is this. Till 3 carbon, no chain isomerism possible. If you add 4 carbon, again 4 carbon, no chain isomerism possible. So if you add 5 carbon, you will try to see if chain isomerism is present on 4 carbon or not. So you can't add 1 carbon here. If you add 1 carbon here, then it will become positional isomerism. It will not become chain isomerism. So you need to add 1 more carbon. So if we add 1 more carbon, now this is positional isomerism. In this case, 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. So same number of carbon, same molecular formula, but different number of carbon present in parent chain. So this minimum 5 carbon will be needed for showing chain isomerism in alkyne. What about positional isomerism? It is simple. 4 only. We have already seen. And in this case, minimum 4 will be needed. So 4 carbon will be needed for showing positional isomerism. I hope this question is clear. In the case of alkane, for chain isomerism, we will need 4 carbon. For position isomerism, we need 6 carbon minimum. In the case of alkane, for showing chain isomerism, minimum 4 carbon will be needed. In the case of position isomerism, minimum 4 carbon will be needed. In the case of alkyne, in chain isomerism, minimum 5 carbon will be needed. In position isomerism, minimum 4 carbon will be needed. Now we'll see how to calculate the number of structural isomerism. Write your NEET. Calculate total structural isomers possible. Isomers possible for following. Now, how to do this type of question? In this type of question, first you need to find DOU. So first in this type of question, first find DOU. What is DOU? Degree of unsaturation or index of hydrogen deficiency. Same thing. So what is the formula of DOU? DOU is equal to C plus 1 minus H plus X minus N by 2. What is C here? Number of carbon atom in the compound. What is H here? Number of hydrogen atom in the compound. What is X here? Number of halogens in the compound. What is N here? Number of nitrogen in the compound. This is the formula of degree of unsaturation. So to calculate the structural isomers, total structural isomers of any compound, first you need to find the degree of unsaturation, and this is the formula of degree of unsaturation. Now, if degree of unsaturation is equal to 0, it means compound is acyclic, is an open chain compound. So all the structural isomerism will be possible in open chain compound. If degree of unsaturation is equal to 1, it means in the compound 1 pi bond will be there or 1 ring will be there. If degree of unsaturation is 2, what does this mean? In this means in the compound either 2 pi bond or 1 pi bond and 1 ring or 2 ring is present in the compound. These are the possibility if degree of unsaturation is 2. Next, if degree of unsaturation is 3, so what is the possibility? Possibility is 3 pi bond is present or 2 pi and 1 ring or 1 pi and 2 ring or 3 ring. These are the possibilities if degree of unsaturation is 3. Next, we try to draw all the structural isomers. First, we will see for C4H10. First, we will see for C4H10. First example, C4H10. Now in the C4H10, what is degree of unsaturation? Degree of unsaturation will be 5 minus 10 plus 0 minus 0 by 2, that is equal to 0. Degree of unsaturation 0. It means it will an open chain compound. So if it is an open chain compound, so one structure is possible. This one. This is one structure. Another structure is this one. So how many structure isomerism possible in this case? A, B, C, D. 4 structural isomers? No, it's wrong. B and C and A and D are same. So only 2 structural isomers are possible. In this case, A and D and B and C are same structural, same. They are not different. Their connectivity is not different. So they are same. So only 2 structural isomers are possible. So total structural isomers of C4H10 is 2 only. Next, we'll C4, C5, H12. In the case of C5H12, what will be degree of concentration? 5 plus 1, 6 minus 12 plus 0 minus 0 by 2, that is equal to 0. In this case also, degree of unsaturation is 0 only. So it has also open chain structure. So one structure possible is, see, there is no formula to calculate the structural isomers. So you have to draw all the structural isomers possible. 1, 2, 3, 4, 5. There is one possibility. Now we take 4 carbon. In this case, we have taken 5 carbon as a parent chain. 4 carbon plus 1 substituent. If you place this substituent here, it will become same only. If you place this substituent here, it will become 5 carbon parent chain. Next, we will take 3 carbon parent chain. 3 carbon parent chain plus 2 substituent. Any other possibilities? So in this case, total structural isomers will be is 3. Next we will see for C6H12. C6H12. If we see C6H12, degree of unsaturation again. Degree of unsaturation 7 or C6H14. Sorry, C6H14. Degree of unsaturation 7 minus 14 plus 0 minus 0 by 2, that is equal to 0. Degree of unsaturation in this case also equal to 0. It means it will be an open chain compound. So we draw all the structural isomers possible. 1, 2, 3, 4, 5, 6. 6 carbon parent chain will take. Then 5 carbon parent chain plus 1 substituent. We can place this here. We can place this substituent here. 5 carbon plus 1 substituent. Any other possibilities with 5 number of carbon in parent chain is 5 carbon? No. If you place this substituent here, it will become same. If you place this substituent again here, these both compound will be same only. Now we take 4 carbon parent chain. So 2 substituent will come. 4 carbon plus 2 substituent. Any other possibility with 2 substituent? No. Okay. These 2 substituent on the same carbon. 4 carbon plus 2 substituent. Now we take 4 carbon and ethyl group. Four carbon plus ethyl group. Now any other possibility is there? 1, 2, 3, 4, 5. Which same? Okay. 5 carbon 1 substituent, 5 carbon substituent can be placed here, 4 carbon 2 substituent, 4 carbon 2 substituent can be placed on the same carbon, and 4 carbon if you place ethyl group here it will becoming same 1 2 3 4 5 here 1 2 3 4 1 2 3 4 5. So this 1 2 3, so 1 2 3, this is already present. Any other structural isomers possible? If we take 3, is not possible. This already we have taken 1 2 3 1 2 already taken. So only 5 total structural isomers possible for C6H14 is 5. Total structural isomers possible for C6H14 is 5. Now in this case, suppose this is A, this is B, this is C, this is D, and this is E. So A and B are what? Chain isomer or position isomer? They are chain isomers. Parent chain is different now. In this case, in parent chain, there are, in this case it is 6 carbon, here it is 5 carbon. So A and B are chain isomers. A and C are also chain isomers. A and D are chain isomers. A and D are chain isomers. If you see B and C, B and C are positional isomers. Position is different, na? Position of methyl group is in this case is second position, and position of methyl group in this case is third position. Number of carbon atom in parent chain is same. So B and C are positional isomerism. Similarly, D and D are positional isomerism. Next we will see for C3H6. C3H6. So if you draw, like first you need to find DOE. DOE for degree of concentration for C3H6 is 4 minus 6 plus 0 minus 0 by 2, that is equal to 1. It means degree of concentration is 1. It means either 1 by 1 or one ring is present. So one ring is 1 by 1. In the case of pi 1, it will have open chain structure. So one structure possible for this is this, and one ring. So these are another structure possible. These are ring chain isomers of each other. So total structural isomers possible is 2. Total structural isomers in this case is 2. Next we will take C4H8. C4H8. Now if you calculate in the case of C4H8, degree of concentration, that is equal to 5 minus 8 plus 0 minus 0 by 2, that is equal to 1. So it means in this case also either 1 by 1 or one ring is present. So when pi 1 will be present, then it will have open structure. So first we will try to draw all the structure containing pi 1. So what is the possible structure? This is the one structure. Another structure possible will be this. Another possible structure will be this. Any other possible structure? If we draw like this, it will become same. So only these 3 are possible structure. Next, ring. With ring we will see. So we can make 3-membered ring also, 4-membered ring also. First we take 3-membered ring. In this case 3-membered ring, one methyl group will come here. So only this is the possibility. The 3-membered ring. Next we will see 4-membered ring. So these are all possible structural isomers of C4H8. So total structural isomers of C4H8 is 5. One DOE degree of concentration is 1. It means degree of concentration is 1. So one pi bond or one ring is present. When pi bond will be present, it will have open structure. So if pi bond is present, these are the possible structures. And one ring is present, so we'll take 3-member ring. So this will be the one structure. If we take 4-member ring, this will be the structure. So total structural isomers will be 5. Now A and B, if we suppose this A, B, C, D, E. A and B, positional isomerism. B and C, chain isomerism. A and D, ring chain isomerism. B and C, ring chain isomerism. B and D, ring chain isomerism. C and D, ring chain isomerism. Next we will see 6 is important. C3 and 6O. In the case of C3H6, what is the degree of unsaturation? Degree of unsaturation is again 4 minus 6 plus 0 is 0 by 2, that is equal to 1. Degree of unsaturation is 1 only. It means either one ring or one pi bond is present. So when pi bond will be present, it will have open chain structure. First we will see for pi bond. One pi bond is present and this alcohol as a functional group. This will be the one. These 3 structures are possible with pi bond. Another structure it can be. Now we can change the functional group. This is another ether possible. With pi bond, only these are the structure possible. Now we'll see with 3. So C3H6. So we can draw 3-member ring. One alcohol will be here. This is the possibility. Now if we draw 3-member ring with oxygen in the ring, so one alkyl group will be left. We will attach the alkyl group here, CH3. Now another possibility will be 4-member ring. Now here we have taken carbon-carbon double bond. We can also take carbon-oxygen double bond. The possibility in this case will be carbon-carbon double bond, carbon-oxygen double bond and ring. These are 3 possibilities. So we have taken carbon-carbon double bond and we have taken ring. So we take next is carbon-oxygen double bond. These are the possibilities. CH2, CH3, again CH3, CH3. So total 9 structural isomers possible for this compound. Total structural isomers possible is 9. I am given one question you have to do in homework. Homework, do C4H8O. How many total structural isomers possible for C4H8O? Answer is 25. For this total structural isomer is 25. Try to draw in your copy. Next, Question: calculate total number of benzoid structure, or you can write, okay, calculate total number of benzoid structures possible for the following compounds. So I will keeping you one compound C7H7O. C7H8 and O. We have to calculate the total number of benzoid structure possible for this compound. So we calculate degree of unsaturation. Degree of unsaturation in this case will be 8 minus 8 plus 0 minus 0 by 2, that is equal to 4. So benzoid structure means in the structure benzene ring will be present. So benzene ring will be present, and you know that benzene ring has DO equal to 4. Now here it can be OH and CH3. This is the one possible structure. Another possible structure for this compound will be OH and CH3 will be here. These two are positional isomers. Position of CH3 is changing. One possible structure isomers for this compound will be OH and CH3. One possible structure for this compound will be OH and CH3 at same carbon. One possible structure for this compound will be OH O CH3. Any other structure isomer possible? Any other benzoid structure possible? No. So total structure isomers in this case will be 5. Next I am giving you one more example. C6H4Cl2. Find the possible structure isomers possible for this compound. So if we draw possible structure isomers for this compound, C6H4Cl2. So one possible structure isomers will be this Cl at this position and Cl at this position. Another possible structure isomers for this compound will be Cl here and Cl here. Another possible structure isomers for this compound will be this is not possible. So we will have total structure isomers 4 1. Cl here and Cl here. These are the only possible structure isomers for this compound. So total structure isomers will be 3. Next we are going to calculate structural isomers in C6H3 BrCl2. So again, if you calculate degree of unsaturation in this case, it will come 7 minus 3 plus 3 minus 0 by 2, that is 4. And you have to calculate only benzoide structural isomers. So one benzene will be there. It will be here. You can attach these two Cl here and here. Now one Cl you can move here. Br. This Cl you kept here, and this Cl you can move here. Again, one structural isomer is possible. This Br here, Cl. We fix this Cl. Now we can move this Cl here. Another structural isomer is possible. Br here, Cl here, and Cl here. Now we will fix this Cl and we will move this Cl. So we fix this Cl. This will be Br, Cl, and Cl. These are another structural isomers possible. Any other structural isomer possible? Br, Cl, and Cl. These are the 6 structural isomers possible for this compound. So total structural isomers is equal to 6. See, for structural isomers, you have to draw all the structure possible. There is no formula. So in this case, total structural isomers is coming 6. Fourth question we will see. C6H2FCl3. Now draw all the benzoidal structure for this compound. If you try to draw all the benzoidal structure for this compound, it will come. We fix this F here. It will be Cl, Cl, and Cl. Again. Fix this 2 Cl and move this Cl. If you move this Cl, it will become this compound. Fix this. We have fixed this 2 Cl. Move this Cl. It will become this compound. Now we will fix these 2 Cl and we will move this Cl. Another structural isomer is possible. F Cl, Cl, it is same one. So this will be Cl, Cl, and Cl. There is another structural isomer possible. Another structural isomer possible. F Cl, Cl, and Cl. This is another structural isomer possible. Now another structural isomer possible is F Cl, Cl, and Cl. This is another structural isomer possible. These all are different, I think. No, these two are same only. FCl, Cl. Then we fix. We are moving this Cl here. We move this Cl here. Now we can draw this Cl, and this Cl here. Now all are different in this case. Yes, all are different. So total structural isomers in this case will be 6. I will give one trick. Trick is that now if this compound is given, trick, this compound is given. In this compound, we have to add substitute. If we substitute, one y, only y. So how many structural isomers are possible? We will substitute this y at this position, and this position. The total isomers are possible is 3. So we have to substitute 2y. So isomers possible are 6. If we substitute 6y, 3y. Here, this F is fixed, 3y we are substituting. So isomers possible are 6. If we are substituting 4y, then isomers possible are 3. And we are substituting two different y and z. So total isomers possible are 10. So your homework is question number 5. C3, C6, S3, F, Br and Cl. We have to draw all the benzoidal structure possible. Draw all benzoidal structure possible for this compound. Structural isomers for this compound. You know, answer for this will be 10. You have to do this in homework. So structural isomery is completed. Next class we will study geometrical isomery. We will start geometrical isomery.